tomorrow evening, to discuss projects that you've been working on, or to show your posters again, especially for those who displayed them in the first week and had trouble communicating with people because they're too noisy in the upstairs room. There was a suggestion of having some chance to present posters again. So can I see a show of hands of how many people would like to talk about any project they've been doing here for maybe 10 minutes using the Blackboard tomorrow night? Not much interest. One person? Okay. I could talk about the resolution, our proposed resolution of the Dresden paradox. I've been working on a little bit. How many people would like to show posters again?
Can we do slides?
Yeah, I think so. Yeah, we could fire up the. Okay. So you'd be interested in talking? Maybe for 10 minutes or so. Yeah. We have 2, 3. Anyone else for talking for?
So you the same poster presentation as previous week, or
If you want to show your poster again, if you feel like there are people that didn't see it, and you'd like them to see it. You know, the poster boards are still up, so we could try to find the pins again and post them. So I feel sort of badly about people in the first week session. It was just too loud to hear along. Okay, so if you're interested, then I think we probably have enough. So please write in the projects channel, just so I know the names, and maybe just give me a subject of what you want to talk about or what poster you want to show. And then I'll get a sense for how much time we can allocate to each person. All right, thank you.
Okay, so last time I talked a lot about the hydrodynamics of slender filaments with the aim of trying to understand how bacteria and sperm and paramecia, how do they swim? How do they use drag to propel themselves? And I thought, as a quick review, I would suggest a homework problem, which I'll put in the notes later today, where we can be a little less hand-wavy than I was when I introduced resistive force theory. I gave this kind of very simple scaling argument. Remember, first we'd use dimensional analysis to say that if you have a long, slender rod where the radius is b and the long radius is a, we used dimensional analysis to argue that there was very little dependence on this thickness. And then we kind of added up a bunch of Stokes slips along the center line to see that the mobility has this logarithmic dependence. And you can do that in a slightly less hand-wavy way, in a way that I think will help tell you what slender body theory is and why that does better. So the idea, or the homework problem, put a uniform distribution of slits on the center line and calculate the velocity from that uniform distribution of Stokelets. In other words, get the mobility, get the relationship between the velocity point and the forces per unit length. Now, the fact that this would be a uniform distribution, of course, is going to break down near the ends, but it's a very good approximation when we have something which is long and slender. So if you do that, you'll get an integral. You can take the limit when A is very large compared to B, and you'll get that leading order log term that I wrote down last time. And then what you could do is you could look at the velocity you get here. Let's suppose that the forces are all pointing in this direction. So you could calculate the velocity at the top of the rod and then calculate the velocity on the front of the rod. And you'll find that it's a little bit different, which can't be so if it's a rigid body. And remember last time we started out saying that the flow of a sphere is really a Stokeslet plus a doublet, and you need the doublet to get the right boundary conditions for a rigid body. So that motivates us to put in a doublet, that source dipole here, to fix up the boundary conditions. And then you can keep going. You can give this a little bit of curvature. And the formulas that I did not write down, the slender body theory, the more accurate theory for dealing with the drag on a, allows you to deal with, say, the curvature of the rod. And what you do is you use this theory that I'm describing here, and you sort of look at just region point of interest, and you break, and then you put everything else into another integral that you have to integrate over. And I won't go through those details. That's what I showed you when I showed you the comparisons of the different versions of the local theory, the resistive force theory, and the slender body theory. Okay, so are there any questions last time? Or any more questions from last time, I should say? Okay, so here's what I'd like to do today. I'm going to talk about some really highly idealized models. Taylor and Lighthill, from the theory point of view, really started the theoretical analysis of swimmers. And they were motivated by talking to zoologists, and Gray in particular, I think, although I don't know the history very well. These are not very accurate, but these are very useful for intuition. Have been used in many, many papers. They're still used in many, many papers, and they help us organize our thoughts about the different effects that are there. I'll talk about the reciprocal theorem again. We'll use this as a shortcut. I mentioned last time in Stokes flow, because of the linearity, there are many, many shortcuts that you can use to calculate things easily. And we'll apply this to this Lighthill squirmer. And then we'll come back to the singular solutions that I mentioned yesterday and focus in particular on the stresslet, which Batchelor in particular used a lot to study suspensions in the 70s. And we'll see that this stresslet is exactly what leads to this active stress that we've been seeing in the other talks, in Suzanne's talk and Julia's talk. We'll just come at it from a slightly different direction and make contact there, and end up tomorrow's lecture with the continuum theory for a bunch of swimmers. Okay, so that's the outline. I always have trouble with this blackboard. I guess it's okay. So let's talk about the Taylor swimmer. So this is 1951. And the idea is that, as I mentioned last time, he wanted to understand how is it possible at 0 Reynolds number, or 10 to the -3, which would be a typical Reynolds number for a mammalian spermatozoan, how is it possible to use drag to get propulsion? So he idealized this problem. He replaced this by something that's not finite, but something which is infinite, just a waving sheet. So this is the Taylor sheet, and it goes on and on and on. There's no head, no tail. And what we have here is a wave, and the material points of the wave are just going to go up and down. So if we're in this frame of the swimmer, we have the height of swimmer. Let's call this point S for swimmer. There's a point on the material point on the swimmer, XS and YS. Okay, and it's a traveling wave. So h of x of t is a traveling wave, which we're going to say is moving to the right. So the material points are moving up and down. And Taylor's question was, if you say that this is sitting in some viscous fluid, so there's some viscosity here. It goes 30 cents. I got this chalk for $2. So we'll say that this is swimming if far away. So up here somewhere at, y going to infinity, if there's some velocity in that direction. We'll have to figure out what direction it is. It seems like, right? So we're working in the breast frame of the swimmer. And to make, so all he did is he solved the Stokes equations. Subject to this boundary condition, which we don't know. We don't know what V is. So it's a little bit like an eigenvalue. It's kind of reminiscent of an eigenvalue problem in the sense that we have a linear thing that's controlling everything, but we're going to have to solve a nonlinear equation to get the swimming speed. Yes. It's a sheet. It's a deformable sheet. It's a sheet coming out this way. Thank you. Yes. So we're going to, for now, we're just going to focus on a two-dimensional object as opposed to a filament. We could do the same thing for a filament. It's a little more complicated. I'll come to that. So the Stokes equations are linear, but the swimming problem is a nonlinear thing because what we have to do is we have to solve the Stokes equations, which are linear, by imposing the no-slip condition at the surface of the swimmer. So the no-slip condition in the frame of the swimmer is that these material points are just moving up and down. So that would be y hat times the time derivative of, of h. Well, maybe I should say a little more explicitly. So this way, so you can see the nonlinearity. The nonlinearity is coming here because v is depending on h. So that's the sense in which we're going to have to solve a nonlinear equation. So to make progress on this, what Taylor did is he said, let's just say this is a simple traveling wave. And he worked in the limit that the amplitude is small. Okay, so his approximation is that the amplitude is small compared to the wavelength. And then he does a kind of, perturbation theory, just an expansion. He's going to expand V in powers of this parameter. So of course, when the amplitude is equal to 0, there's no swimming speed, nothing happens. And there's a first order piece proportional to BK and a second order piece. It turns out that this is as high as we need to go to get to see something. So we can kind of see what's going to happen. First of all, the velocity, swimmers can, I showed pictures last time of, I'll show some more today of, I guess I sketched Chlamydomonas, right, where it has its stroke, which is going like this, and then it has its recovery stroke where the cilia kind of fold up and they come back and it actually moves backwards a little bit. So the speed is not steady. So this doesn't apply here. Here the speed is steady in this very simple model because, if we shifted the origin of time, that's just like shifting the origin of space or shifting the origin for the x-axis. And because it's infinite, that shouldn't change the swimming speed. So the swimming speed is going to be constant in time. The second thing we can say is that if we replace the amplitude by its negative, so imagine just flipping it, all we're doing is we're shifting the swimmer by half a wavelength. And again, because it's infinite, we wouldn't expect that would have any effect on the swimming speed. And you might worry, well, maybe it goes like the absolute value. It doesn't go like the absolute value. It turns out that the swimming speed is an even function of the amplitude. So that's why Taylor had to go to second order in this amplitude, because to first order, when you solve this problem, we just have the material points going up and down and you enforce this boundary condition on the x-axis, you don't get any forward swimming. So I'm running out of room, so let me go over here. So to that end, let's see, what else can we say before actually, yes?
Velocity on the filament, velocity on the filament.
This is the no slip condition here. So here's the fluid velocity V of X and Y. So I'm evaluating it at the filament or at the sheet at the height Y. And then I'm saying that's equal to the velocity of the sheet. So this is the no slip condition here.
Oh, okay, and that's in the moving frame of the.
In the moving frame, in the frame in which the material points are moving up and down. It's not an extensible sheet. It's, well, so we're going to have to self-consistently find out what the velocity is far away. So the way that we decide is that it's swimming is we look at the sheet, we say we're in whatever frame we need to be in for which the material points are moving up and down. And if we see far away the fluid is moving this way or that way, then it's swimming. Okay?
Far away from the.
Yeah, this is very sloppy. Yeah, far away. That's our other boundary condition. Yeah. Yeah. Sure. Well, what that says is that the fluid particles have to move up and down right here. That's a very good question. It's a very good point. So what's interesting, I think, about this problem is that even though the fluid points, which are right next to this sheet, they're moving up and down, somehow we get horizontal motion. It's not apparently obvious right away, I think. I think that's a perceptive question. But that's part of what Taylor wanted to see. Okay?
So this type of motion does not involve the cycle in the space to overcome the non-reciprocity.
Well, it does in the sense that it's a traveling wave. So the traveling wave, there's a cycle in the sense that, you go from, in one period, the shape looks the same. So, if you took a movie and ran it backwards, you'd be able to tell that you were running it backwards. So it's breaking the time reversal, or, it's a non-reciprocal stroke. Okay, very good. Good questions. So let's use dimensional analysis. To see what V is. The Stokes equations are linear, so the speed has to be proportional to the frequency. We know that that has to be true. I also argued that it has to go like the amplitude squared. So the only thing we have left is the wave vector. I could also write this as b squared k squared times c, where c is the speed. By dimensional analysis, the leading order in B, the speed should go like b squared k squared times the wave speed. And remember, and this is kind of a typical thing, we're working in the limit where b squared and k squared is small. The swimming speed is going to be small compared to the wave speed. So then Taylor did the calculation. He solved Stokes equations. And the key thing is this expansion that I wrote down over there is you have to expand the boundary condition at the sheet. You have to say that V of X and H, I have to expand V and I'll evaluate it at X and H. So I expand the function V in powers of B, K. And then I have to expand the arguments, this kind of boundary perturbation that we often have in deformable problems with deformable boundaries. So I want to, put the boundary conditions where it's easy to evaluate, like on the x-axis. So I have to, I have to expand. And then I have to take the derivative of the first order flow with respect to y and multiply it by the height and then evaluate that at x and 0. And then to second order, I can just evaluate the second order boundary condition at the x-axis at y equals 0. So when Taylor solved the first order problem, he solved the Stokes equation with that boundary condition, just saying those material points are moving up and down. But in the second order problem, you have to be careful. You can't just say, you know, there's another piece that comes from the first order problem. And that's where the nonlinearity is arising. The upshot of all of that is that you get a half. You get a half, and you get that if the waves are moving to the right, now let's go to the lab frame. If the waves are moving to the right, that means that the swimming speed is to the right. So, you know, if you're in the frame of the swimmer, then the flow upstairs would be going the other way. Okay, so that's Taylor's calculation. And the direction of swimming, I think, is very interesting. It goes, you know, when I first saw this problem, I said, of course it goes in that direction, because I have this intuition from being a person who is not a very good swimmer, but I can swim. And, you know, if you push against the water, you'll go opposite. But that intuition is based on imposing, you know, giving inertia to the liquid. And doesn't apply here. And it's actually subtle. I think it's subtle to understand the direction, and to see that it's subtle. Could look at a different problem, which Taylor also looked at, which is a longitudinal wave. What did I do here? Is there another board that goes? Oh, this one goes up. Ah, thank you. Very good. Excellent. So this is a transverse wave. We could also imagine a longitudinal wave. Longitudinal wave, where the material points on the surface are only moving, you know, the surface is stretching out and compressing in the horizontal direction. So I'm drawing the displacements. And, you know, you could write down a wave. So now instead of having a height, you know, the ys be vertical for the displacement of the sheet, I could have it be horizontal with a wave. And you could work out, you know, instead of a y derivative here, you'd have an x derivative, and you could work out what the swimming speed is. And what I think is surprising is that in the lab frame, if the waves are moving to the right, for this swimmer, sorry, what did I do here? No one gave me a hard time about this. Did I draw this wrong? You would expect it would go the other way, wouldn't you? Okay, thank you. It's the fourth week. Even I'm tired, but I've only been here for 2 weeks, right? If the waves are going this way, it would go the other way. That's what you would expect. But in the longitudinal case, it goes in the same direction. So I think this is subtle. I think it's hard to understand. I don't really have a good way of understanding it except drawing pictures. And really, these pictures are just pictures of the mathematics. It's a little bit of a cheat, but it gives you a hint of the direction. So what we have here is a snapshot of this deforming sheet. So you see these arrows. So you see these, this is the first order flow. This is the V1 that you can solve, or that Taylor solved. So you see over here, the arrows are moving down. That means that because of the no slip condition, that means that the wave is moving to the right. But remember, the material points are moving up and down, completely vertical. So you can see the first order flow is a little bit wrong here, right? So of course, it obeys the first order condition, boundary condition exactly. But you see up here on the top, the flow is moving to the left. So this piece here from the second order flow, there's a piece that involves the first order flow and the deflection that actually corrects this when you get up here and there's a flow to the right, meaning that very far up here in the second order plus first order flow, the flow is going to the right so that the the waves are going to the right. So that means the swimmer is going to the left. So you can kind of look at the flow in detail and figure out which direction it should swim. It's harder to do for the longitudinal case. I have the reference here in the notes, but you can do it. And it's sort of like doing the crossword puzzle. You have to remember that. So in this case here, the flow is, or rather the wave is going to the right. And you have to remember that if, you're enforcing the no-slip boundary condition here, let's say that the displacement at this instant is a sine wave, the displacement at this point is a little bit to the right. So you have to say that the velocity is zero, the horizontal velocity is zero, a little bit to the right of this point, which means that it goes, the second order piece that corrects it goes the other way. So the point of showing this is just to say that it's a little bit subtle to figure out what the swimming direction is. I'm going to turn this off, but I'll keep this on if there are any questions at this point. Okay. Okay, very good. Yep. Yeah.
That is the same of that capital V.
No, sorry. Omega over K is the wave speed.
So what is, I'm trying to understand the difference between capital V, that's the.
Yeah, capital V is omega over K, the wave speed, times this amplitude with a numerical factor. So the swimming speed, actually, maybe I could just show it here. The relation is that you've got this wave speed, which is C, which in this case is moving to the right, but the material is moving up and down. In this picture, we're in the lab frame. The material points are moving up and down. V, what you're asking about, is this up here. And it's proportional to C. It's proportional to omega over K, but it's reduced by this amplitude squared. So you don't quite, it's yep. Yeah, one way to think about it, actually, you can really think about it in the case of a bacterium where it would be a helix. The helix moves in the direction that a screw would when you screw a screw into wood, but it's as if it's slipping, right? When you screw a screw into wood, it moves one wavelength in one turn. But the fact that we've got this small number here and we have something similar in a helix means that it effectively slips. It's not moving as fast as the wave speed because of this fluid in between.
Is there no slip boundaries? The fluid has the same velocity as the filament?
Yes. Yep. 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 Okay, so I will, I mentioned a couple more, well, maybe not so recent. This is very idealized, but it gets at some intuition, and people have used this to ask about how do different physical effects change the swimming speed. So for example, you could ask, what about the Reynolds number? What if you look at something that's not at zero Reynolds number, but still laminar? You could still do this calculation. We're just doing perturbation theory. We have another term. It's a nonlinear term in the equation now. Everything goes through. And this person, Tuck, calculated the effect of the Reynolds number and found that it actually makes it swim more slowly. And just to make contact, this is one that it turns out asymptotes out to a half, to make contact with what I talked about last time when I mentioned this fact that Stokes flow for given boundary conditions is the flow that minimizes the dissipation rate. You could calculate the dissipation rate or actually Taylor calculated this. It's I don't remember. There's no half, I think. I think that's right. Let me just double check that. Yeah, I think I'm off by, you can check the dimensions. For the case here, dissipation rate is actually greater than this 0 Reynolds number. So that's a simple, it's almost just as easy to do this. In fact, this calculation is not that hard. This is the kind of thing one might put on a graduate fluid mechanics exam. So this is a kind of simple calculation where you can just look at two different boundary conditions, excuse me, two different flows for the same boundary conditions and see, oh yeah, the Stokes flow really does have the least dissipation rate. The other thing I'll mention is that there have been many, many papers, some by Eric Loga, who looked at viscoelasticity. The question of does fading memory in the fluid, if you put in some dumbbells, the Oldroyd B model that Suzanne just talked about, he showed that for small amplitude, the swimming speed decreases. Then there were other people in my group at Brown who looked at filaments, who looked at rotating helices, and sometimes we found that the speed increased. And I won't go into any of those details, but there's a lot of work in figuring out just the fact that the effect of making the fluid viscoelastic really depends on the geometry, whether or not it makes it go faster or slower. One last paper I'll mention is a paper by Leshansky from 2009. And it's about what I would call colloidal effects. Meaning, what if you have a bunch of stationary obstacles? How does that affect the swimming? And again, these are very, this is all in the context of the Taylor swimmer, but there's a recent paper by Kamdar et al. That I highly recommend. With, where they really look at the effect of polymers or colloids in a real experiment, and they disentangle all these different effects that people have been thinking about for several years. And they even have to worry about the fact that the hook connecting the body to the filament of a swimming bacterium it bends so that the body wobbles, all these things. And I think they've really nailed it. They really have put all these things together. So I won't talk about that either. I'm just alerting you to that. There's one last thing I forgot to say. One more qualitative thing I wanted to say that I'll say over here. And that is just, one aspect of the solution that maybe has jumped out at you as something that seems wrong or troubling. And that's that in this Taylor model, the swimming speed is independent of the viscosity. And on the one hand, we can see that had to be true because of our dimensional analysis. There's no room, there's no way that viscosity could enter. The reason is that viscosity doesn't enter is because it's the prescribed swimmer problem. It's a magic, super strong bacterium that's going to do this stroke, B sine kx minus omega t, no matter what the load is. It doesn't care, right? It's like some kind of superhero. That's not that. So that may be true in some range of parameters in a real experiment, but generally, you know, you crank up the viscosity, the motors are going to poop out, right? They're not going to be able to. But it also, there's another way of seeing why viscosity doesn't enter that I think is helpful. I think of it as an intuitive version of the reciprocal theorem, which I'll talk about in a moment. So the idea, and this idea I first read about in Childress's book. So the idea is to use, you know, why is this true? Why is the swimming velocity independent of viscosity for the prescribed swimmers? So the idea is to use linearity and break the swimming flow into two flows. So we can use superposition. So the swimming flow, we'll say, is a thrust flow plus a drag flow. So suppose we've got a swimmer, and I'll just denote the fact that it's swimming by saying that little vs is some kind of velocity on the surface, you know, including the flagella. So vs is maybe moving in time, changing in time, or not. It doesn't really matter. Okay, that's the swimming flow, and then we're going to break this up into a thrust. Oh, okay, so this is swimming. So let's say this is moving to the right. So the thrust flow, the same motion at this instant. So this is at some time equals t0. And this is the same shape and the same swimming distortion, but we're holding on to it with a force. We're not letting it move. So that, I'll just call it V because it's not swimming. That's equal to 0, right? So we just grab onto it at this instant. When it's in this conformation, we grab onto it. And you could solve a little Stokes problem and figure out how this force F depends on Vs, okay? For the drag flow, what we do is, you know, we're what do we say? We're mad scientists, not evil scientists. So we take this swim, freeze it. You freeze it at this instant, or, you know, when it's doing this. So now Vs is equal to 0. And now we drag it. We're going to drag it through the fluid at some velocity. I guess I should use a different color. I'll use green for the color of the pool in front of Buckingham dorm. So that's F, okay? It's just the drag problem. Now, we want to figure out what the swimming speed is. So these have the same, if I add these together, adding the boundary conditions, I get back this boundary condition. So to find the swimming speed, I add that anchoring force that depends on the velocity of the boundaries at that instant to the drag force, but I have a problem to solve. I want to make the total force be 0 because the total force is 0 on the swimmer. So that's how we find the swimming speed in general. So what does this have to do with viscosity? Well, for this prescribed swimming problem, both of these terms are proportional to the viscosity, and the viscosity just drops out. And this argument, you can use this argument in other contexts as well. Okay, so that's the Taylor sheet. Question, yep. That's true. That's true. That's right. The key is it's also that this deformation doesn't depend on eta. So if you put in a model for what the motors are doing, there'd be some load curve where the forces that the motors would exert might depend on the viscosity, or the flexibility of the filament, the fact that it's going to bend in a different way in a different fluid. So that's right. So it's all in the fact that this H, and that's the only place it doesn't depend on the viscosity. That's right. Yep. The tuck work, yeah. So taking the steady, well, actually not steady, just taking the Navier-Stokes equation and doing exactly what Taylor did. It's just that now we have a nonlinear equation as opposed to a linear equation. It's not perturbative in Reynolds. Thank you. Yes, there's some complicated square root that it enters. That's the nice thing about, it's a perturbative thing, but if you look at that problem, or if you look at the problem of Oldroyd B, the way that the Deborah number, the relaxation time enters, is not just a small perturbation. It's an order 1 change to the velocity.
In other words, I mean, I think the divergence of the delta is control, I guess, delta negative.
Yep.
Except it just drops out.
Yeah. Again, but don't forget about the boundary condition, right? But yes, that's right.
Boundary condition doesn't, or, once you separate it,
Yeah, but we need that to get this, right? Yep. Go ahead. Yeah. That will change in time. So this is just some instant in time. At some other instant in time, it goes exactly to what Peter was just saying. The pressure and the vorticity instantaneous. There's no time derivative. It's Laplacian that instantaneously adjust. So we have to solve a different problem at each time to do this argument. That's right. Okay, very good. All right, so I will now turn to the Lighthill swimmer. I'm going to have to rearrange a little bit, but that's okay. All right, so let's start over here. So, G.I. Taylor, lots and lots of insights from a very simple problem. But we'd like a finite swimmer. And now we're going to graduate from 2 dimensions to 3 dimensions. And also, there's some very nice work. Blake in the 70s, who was, I don't remember the exact date. For Lighthill's paper, Blake was Lighthill's student, did a lot of nice work. So the idea is, well, let's start with a sphere. And let's suppose that it's covered with cilia, kind of like a paramecium. So this is supposed to be, there's some beating cilia here. So this is the so-called ciliary envelope. So one idea, about Taylor is that you could think of the tips of the beating cilia as that no-slip surface that we used in Taylor's problem. But now we're going to do it this way. And, we can make a model of this model where instead of having a deforming surface, we could just, I think I wrote this down last time. We could just impose a slip velocity at the surface. So the material points on the surface are just moving tangentially like this. So this is not as grand as Nigel Goldenfeld's hierarchy of models, but it's a model of a model. At low Reynolds number, I argued last time that the shape doesn't make much of a difference. So why not look at this problem? So you could put an arbitrary velocity on the surface and solve the problem. Solve for the motion, either hold it, well, not hold it fixed, but sit in the frame of the swimmer and see what the velocity is far away, or not even do that. Just impose this velocity and say the velocity at infinity is equal to 0 and see what you get. So we're going to use a simple case. Do the most general case. That's in Lighthill's paper or Eric Lauga's book. He worked this out. And these are really the two most important terms. So this is the deformation of the surface. And on top of this, we'd have to add the velocity of the center of the swimmer. Okay, so this is VS relative to the center. VS is the surface. So let's look at these. So we can split things up. So if B1 is, I'll always take B1 to be positive, that looks something like this. And likewise, if B2 is positive, sine and cosine are positive in the first quadrant, they're negative over here, positive, let's see, something like that, right? So this, when you add these together, that means you're getting a lot of push or a lot of velocity up at the top and not as much at the bottom. It depends on the relative value of B1 and B2. But this, if you squint your eyes, is kind of like the Chlamydomonas. This is what we call a puller. So Julia Yeomans mentioned these pullers before. And same thing, if you make B2 be negative, you can go through the, you can draw the drawings where you get the backside, and that's something more like, a mammalian sperm, just very schematically. So those are the kind of the two basic kinds of swimmers that we have. Right, so we can solve this problem by just doing separation of variables. But I wanted, maybe I could do it here. Yes. Other way, we need the B1. The B1 term contributes to propulsion. The B2 term does not. Stay tuned. That's a good question. In principle, there's a bunch of them. Why did I choose just these two? It's because this one tells us about the swimming speed. And it's because this one tells us ultimately what is the stress that this is going to exert on the fluid. That's going to be the stresslet, and that's what we'll need to see how the swimmers interact. So that's why that's the only one I kept. Yes. So imagine it's like a conveyor belt, a double surface. It's the conveyor belt's coming out of the North Pole and just moving out radially down and pushing the fluid that's next to the surface. Yeah, or a whole continuous conveyor. The second one, it's also, well, it's the surface is it's an extensible surface that can deform. And I think maybe the way to think about it is, you could imagine that happening here because by having the tips of the cilia can be doing that motion. Okay. Okay, so there's a very nice paper by Stone and Samuel. Where they use the reciprocal theorem. which I wrote down, I guess I'll write that down again. So this is generally have whenever you have linear governing equations. So you have two problems that have the same geometry but different boundary conditions. In that case, the mixed rate of working, meaning you take the stress of one problem and you dot it with the velocity of the other problem, that's the same for the two problems. Well, these quantities are the same. So I don't think I'll go through it. I was going to go through it in the interest of time. I'll just kind of tell you what the problems are, and you can do it yourself. So problem one is the Stokes drag problem that we talked about last time. So you have a velocity because you're dragging the sphere with some force. And it turns, I don't know of a really simple way to see this other than just calculating it. But it turns out that the traction in the Stokes drag problem is constant. It's very simple. So you can figure that out. As long as you know that it's constant, it's easy to remember what it is. So it's let's say the horizontal direction is x hat. So I just divide that force by the area, and that tells me what the traction is. So you have to do a calculation to see it. But the fact that the traction, the stress dotted into normal on the surface for this spherical problem is constant means that this is very simple. That's why it's easy to use the reciprocal theorem, or that's why the reciprocal theorem is a shortcut to finding the swimming velocity. Problem two. Problem two is the swimming problem. It's the problem we want to solve. So here, on the surface in problem one, everything's moving with the same velocity. In problem two, it's doing that. It's doing the VS. Or rather, how did I write this here? Yeah. So let me just write it this way. So the velocity on the surface, R equals A, is the superposition. It's the swimming velocity, which we're trying to find, plus the velocity I wrote down over there. Okay. So you can have fun with this. The key point here is that the force on the swimmer is equal to 0. So because V1 is constant, this term gets wiped out. Then over here, you have a constant times something involving the swimming velocity. Actually, I guess I did just do it. So I just did it. So the end result, that's all you have to do. The end result is that the swimming velocity for a sphere with this prescribed motion is basically the average of that surface velocity, which turns out to be 2/3 times B1 times Z hat, the B1 there. So you can do that. So that I thought that was very insightful. Stone and Samuel found the swimming speed without solving for the entire flow field. And this idea is, again, led to many other ideas, but this is like a fundamental basic idea. I'm sorry? 1996. That's an excellent question. I think it's exactly, why what I said last time. Why am I working on it? I think it's because in the 90s, the theorists were saying, oh, look, there's all these experiments that people are doing. You could apply fluid mechanics more. Of course, people have done this for years. Taylor, Lighthill, many people in the 70s, but because of the experiments, more people started thinking about this. I don't know why no one thought of this. Actually, probably someone did, but That's the first publication I know about. Oh, sorry, yes. So we have, it has to do with the linearity. That's key. You have to have the same geometry. I think that's it. So we have this in elasticity theory. It's like Green's theorem and electromagnetism, same kind of thing. Okay, so yeah. So now let's, now what I'd like to do is just write down Lighthill's solution. Sort of schematically. So the full solution, you just have to bear with me as I write this out for a moment. I'm actually not even going to completely write it out, but the full velocity looks like this. So, you know, if you wanted to solve the problem, you'll see while I'm writing this out in a moment. I'll use our tensor notation. And then there's one more term. This I won't even write out. There's some tensor here that you can work out. Okay. So why did I write all these terms out? So you can see you have the uniform flow. We saw this last time. This is a dipole, a source dipole, or a potential dipole. If z it's oriented this way, if z is up, we needed that in the solution to Stokes. This one is new. This one is called the stresslet. That's the leading order term. It goes like 1 over r squared. And this last one, if you differentiate this, you'll get this. You know, if I had written out what Q is, this is the source quadrupole. And again, this is an axisymmetric swimmer. I won't get the overall sign right, but it's something like that, right? That you've got two dipoles, source dipoles in the opposite direction at the center. There's no Stokeslet. So there's no Stokeslet because if there were, then there would be a force on the swimmer. So when Lighthill solved the problem, or when you solve the problem, you write down you solve the differential equation, you write down all the possible solutions, you impose the boundary conditions. You need one more condition to completely solve the problem. The one last condition is that the force is equal to 0. So Lighthill had to impose that. That's a little different than the Taylor problem. V just came out kind of like, you don't even notice it. It self-consistently comes out. I think, if I remember correctly, if you put the Taylor swimmer near a wall or between two walls and it's not halfway between, then you actually do have to impose this force. Generally, you have to do this when you're solving numerically or analytically. You always have to say 0 force. So what I'd like to do next is show the flow fields that people have measured to see that this really dominates. You know, you can see this goes like 1 over r squared. This is 1 over r cubed, as we talked about before. And the quadrupole, we differentiate again, goes like 1 over r to the 4th. But before I do that, I just want to say a little more about the stresslet. You know what? No, I think now is a good time to show the slides because, yeah. This? All of this? Yeah. So I take Stokes equation in spherical coordinates and impose this boundary condition. And I just look up and I write down all the biharmonic solutions, all the possible solutions that could possibly match that. And that would be these terms, including the Stokeslet. And then we apply the boundary conditions and the condition of zero force. More questions is about to get covered. More questions? Yes. Well, yes, if B2 is 0, we only have these potential flow parts. I wouldn't say there's an out, I should say it is potential flow. It's a curious thing, but just remember that the relationship between the potential flow solutions and the pressure and the stress is different than it is in ideal flow because we don't have Bernoulli. I thought I heard another. Okay, I think we're ready for the. Oh dear. My computer is not waking up here. Is it going to be a disaster if I unplug this? Oh, there we go. Okay, I just was impatient. All right, so let's look at some experiments. So this is from some time ago, but what we're looking at here is the flow field induced by E. coli. So I said E. coli is a pusher. What's plotted here is the stresslet field, just the stresslet, what I wrote down underneath the board. And what they did is first, I didn't emphasize it very much, but maybe the E. coli generally does this random walk, the run and tumble. When their motors are all going counterclockwise, viewed from outside the cell, the filaments form a bundle and it swims more or less straight. And every so often the motors reverse and the bundle flies apart and it reorients. That's a tumble. These swimmers are mutants. They don't tumble. They only swim in one direction. They get knocked off course because of Brownian motion and things like that, other swimmers, but there's not a lot of them. They just wait. And they look at a lot of them and they wait to see one that's swimming in the focal plane. And they look at a lot of them and they worry about maybe some differences in different bacteria, but they average over many, many of these swimmers to get this time average flow field and compare it with the Stokeslet. So the question is, the stresslet. The question is, what is the flow field of a swimming bacteria? So they say it's a stresslet. This picture is the difference between, it's the bottom half, right? So here's the bacterium in this lower picture, it's the bottom half. The red is a difference, the red means a big difference between the theoretical calculation and the observation, and the blue and the green means a small difference. So of course, nearby the swimmer, we don't expect this far field spherical thing to work very well. So this is saying, we're just looking at what is the far field swimming flow field induced by an E. coli. It's a stresslet. I won't talk about walls. I won't talk about boundaries, but this is a very interesting question. How do swimmers interact with boundaries? I'll just show one picture. This is a swimmer near a wall. I don't remember how close to the wall it was, these events. But you can see now these flow lines close. It's very different. So just like in electrostatics, you can work out what this far field swimming field should be by putting an image stresslet below the wall. And as you might imagine, it's more complicated than it is in electrostatics because you're not just making the potential equal to a constant on the wall. You're making the horizontal and the vertical, the tangential and the normal velocities equal to zero. It's harder. So there are other images, not just the anti-stresslet, but that's what's shown there. So they're looking. Sorry. Yeah, they have particles in the flow, and it's a very delicate. There's a couple groups that have done this. This was a real tour de force. That's really all I can say about it. Look at a bunch of them, lots of tracer particles, and averaging over many, many. You might ask for an example of a really spherical swimmer. So Volvox is an algae, and it turns out it's pretty big. That's a 500 micron scale bar, and this is an example of something that does feel an external force. So there is a Stokeslet. There has to be a Stokeslet to balance that external force, so that the total force, external force, plus hydrodynamic force on the swimmer is zero. And that's basically what you see here. Again, putting a bunch of particles in and measuring the flow field. What's interesting about this is they have, maybe not in this picture, but using, again, what I covered up, there was the leading term was a stresslet, and then there's a potential dipole, and then there's the quadrupole. They don't worry about that. What they find is that once they subtract off the Stokeslet, it's actually the potential dipole, maybe to Tali's question, that has a stronger amplitude than the stresslet. It's a very symmetric, this coefficient B2 for these guys is quite small. I think the last example I have here is that even for something like Chlamydomonas, where you've got these cilia doing the backstroke or the breaststroke or whatever, where the flow field is very complicated, you can get pretty far by modeling it as a sum of some, put a Stokeslet at the center of the body, and then somewhere, and there's a lot of work that went into this, put equal and opposite Stokelets of strength 1/2 to represent the cilia, and see you can get a good sense of the flow field that way. Okay, and I think that's all I have for. Maybe I'll put that back up for a moment. Oh dear, how do I see this view? Okay, so I just wanted to establish that these singular solutions, these flow fields that I've been talking about are something that are seen experimentally and therefore worth looking into even more theoretically. But are there more questions on this? The difference in the pusher and the puller flows is the difference in the sign of the stresslet in the far field. So it's both the puller and the pushers in the far field have this flow, it's actually completely radial. The stress, I'll write that down in a moment. But the only difference is that in the pushers, here the head is moving forward. It's like pushing the fluid ahead of it, pushing the fluid behind, and laterally it's drawing fluid in. So if you have two nearby pullers, these are pushers, two nearby pushers, they'll attract each other. Whereas I don't have the same, you just have to reverse the arrows for a puller, right? For a puller, you're pulling the fluid ahead of you towards you. And the drag of the body is entraining the fluid behind it, drawing the fluid in from the back, and then the fluid's going out along the side. That's the difference between the pusher and puller flows. Yeah, it's exactly, we'll see that in a moment, I think. It's exactly the flow for a sphere and extensional flow. Yep. Okay. All right, so let me turn this off. Let's, I think I'll try to finish this up. Okay, so let's, I'm going to talk a little more about the stresslet. Okay, so there's all these tensors. I'll just write some of them out. So the stresslet plus something called the rotlet or the rotelet. I say rotelet. I've heard people say rotlet. I don't know why, but I guess our rotation. That's equal to the Stokes dipole. So there's nothing new here. We take the Stokeslet. Let's say we have a Stokeslet here pointing down. Maybe it's got a force, and just like E to be the direction of the Stokeslet, and then we add the Stokeslet in the opposite direction, and say that the displacement here is some small vector times d. That's the Stokes dipole, right? So it's complicated because you could, it doesn't have to be axisymmetric. You could move out to the side or you could move up. So you can go through this. You could calculate what the flow field for the Stokes dipole is by taking the derivative of the Stokeslet, which is acting on this force F. So G is that tensor, the Oseen tensor, or up to some factor, Oseen-Berger's tensor that we wrote down earlier. We saw in many talks this week and last, the first week. Okay, so you can do this. I'll just write down what the answer is, because it's sort of, I'll write it down over here. Actually, we don't need that up there. I'll write it down here. Yeah, thank you, Leo. So G is the Green's function for the Stokes equation. So, so if we put a point force, which I called capital F here, at the origin, and right, because this is the sum of the forces per unit volume. Sorry, there's a delta function. There we go. So this is a force per unit volume. It's basically just 1 over r, but because of the incompressibility condition, there's something else that you have to add to make it, yes, so that it's, yeah, k dot u, yep, is 0, k dot v is 0. Yep. Okay, so if we write this in index form, you'll see why I'm doing this in a moment. So I'm going to call this the Stokes dipole. So it's got 3 indices because it's a velocity, and then you have to contract it with the direction of the force and the direction of the displacement. Okay, so you can take the derivative, you can work this out, and you can symmetrize and anti-symmetrize it on J and K. That's a convenient thing to do, because that's what gives us the stress in the rot. Okay, so the
Is that VI the same as BSD?
sorry, thank you. So GI JK SD. So there's one bit. So these are all There's 3 x's up here, there's 1 down here. This goes like 1 over r squared, 1 over r squared, like that B2 term in Lighthill's solution. Same thing here. These are all proportional to xi. So that's going in the x direction when you contract it with E and D. So that's the radial flow that we saw. And then there's the antisymmetric part. Antisymmetric in the indices that contract with E and D, right? So this bottom part is the rotelet. And this is the stress slit. So, you know, E and D, if E and D are perpendicular, I'm gonna try to respect my color scheme. You get a little couple. You get a little, you know, little actually point torque, right? And you can see what that torque is. You can see right there, this torque. The torque is going to be LF times D cross E. It turns out if you, I have it worked out in the notes, so you can do it yourself. If you write out this flow field, this rotelet part, for the case where D and E are perpendicular to each other, it exactly satisfies the boundary conditions for a rotating sphere. So this rotelet field, flow field, is exactly the flow field of a rotating sphere. You know, which, you know, how do you have to, you know, you can go through the details. Maybe I'll write it here. So M I've actually given you enough to work this out. You can check that when D and E are perpendicular, that the velocity on the surface of the sphere is constant, or well, not constant. You know, it has the velocity you need for a sphere, right? It goes like sine theta. So it's a little bit like the Stokes slit. Remember, we said that the flow field induced by translating sphere is a Stokes slit plus a doublet part. The A gets very, very small. Here it's all rotelet for a rotating sphere. We'll come back to that later. Of course, there's no torque on a squirmer, so that's why this solution didn't arise.
Lost physically, what is this describing? What type of
So this, what I'm saying is that I'm trying to get at the stress slit. You know, last time we said, and you weren't here, so we generated all these singular solutions. We started with a source, took a derivative, got a potential, took a derivative, got a quadrupole. And now I'm doing the same thing with the Stokes slit solution to get the Stokes dipole. I'm saying that part of it is the stress slit. That's what we saw in Lighthill. The other, I'm just saying there's another part, which is the rotelet, which we don't need right now. Okay, so this other part is there's one sort of tedious thing I want to do. This, if we look at the stress slit, it's often written this way. So you see here, it's all going radial. And, you know, there's just some algebra that you have to go through here to write it this way. We're just writing it a little more generally, where S is a tensor. I'll write it in terms of indices. So you can take what I've written up there in terms of E and D, do a little bit of massaging and write it this way. S is called the stress slit tensor. You can see here that S is symmetric, right? The antisymmetric part is not going to do anything. It's also traceless. It has to be traceless to make this stresslet have no divergence. That's sounding kind of familiar, right? You get this, the stresslet flow field can be written using this stresslet tensor, which is a traceless symmetric tensor. And that just comes out of the, it's just a fact. Okay, maybe we won't early. So I want to make one last point. So or two last points. Once we arrive here, we can ask, what is the contribution of a bunch of swimmers to the mean stress in a flow field, or in a, I don't know, a suspension of swimmers? So many people recently have been talking about things like the swimmer pressure and the swimmer stress. These ideas are very old. Well, I guess it goes back to Batchelor. So Batchelor asked the question, what is the mean stress in a dilute solution of particles? And I won't go through you can go through the calculus. Again, it's in Eric Loga's book. He does a really nice job. So you have a bunch of swimmers, but it's dilute. And what we want is the mean contribution to the stress from the particles. So the particles could be passive. Batchelor was thinking about suspensions of, particles that were not swimming, or they could be swimmers. They could be active. So this mean contribution, we're going to call it capital sigma. So Batchelor says, well, just take the average stress over the volume, including the insides of the cells. Now there's some steps which I won't go through, but the key step that Batchelor makes is he uses the diluteness. So he uses Stokes' equation, he uses Gauss's theorem to convert this integral over a volume into integrals over surfaces, meaning the surfaces of the particles or the surfaces of the swimmers. And then he uses the dilute assumption of diluteness to take those integrals over the surface and put them as integrals over big spheres of radius, let's say radius R1. Well, when you do that and you take that velocity field over there and you calculate the stress, it turns out that this the contribution from the swimmers and just the deviatoric part, the part that's traceless, is the sum over all the swimmers. So I don't know why I use sigma for the stress, probably because that's what everybody else does, of S. So this traceless symmetric tensor, the stresslet, that is the contribution of all these particles to the mean stress. So if you want to make a kind of continuum model, that's what you would do. I could write this as the particle number concentration times the sum over all the swimmers of Sij. And of course, if you've got a swimmer, an axisymmetric swimmer that's got some orientation vector P, what is S? Well, Sij is going to be proportional to delta Ij over 3 minus Pi Pj. So that's the Q tensor. We have to do a little, we have to worry about the density and things like that. But that's basically the Q tensor that Julia introduced in the very first week. So okay, I guess I'll leave this as an exercise. Because I can tell even I am getting hungry. Yep. This is for any swimmers in the volume, yeah. So I'm saying we've got a collection of swimmers, all the swimmers in the volume. Oh, sorry. So yeah, all the swimmers in the volume. So maybe this is not the entire volume of your sample, right? This is maybe the whole universe of the suspension is bigger. Exactly. That because of the diluteness in this step, the key step of saying, let's simplify the mathematical calculation by putting the stress on this surface. The only thing that survives is the leading term in the far field, which is the stresslet. So pusher puller. Yep. Okay, so the last thing, which I think is kind of neat, is that you have everything here to do another famous calculation from 1908, Einstein's calculation, which this is not the way he did it. But, you know, if you have a shear flow, you can break that up into a rotational flow. Let's see if it's going to the right. If it's going down over here, it's got to be going up here, and it's got to be going, you know, it's going up here, so it's got to be going down here, and it's right. So you have an extensional flow. So if you have a sphere in a shear flow, you've got rotation and you've got extension. Someone asked about this already. So when you solve the problem of a sphere in the extensional flow, you get a stresslet. When you calculate, now suppose you have a bunch of these spheres, you can figure out what the contribution, what the particle contribution of those spheres is to the stress. And, you know, I worked out all the numbers here, but the upshot of all this, let me just say it this way. You can show, let's say that the strain here is EIJ. In other words, this is terrible. VI is EIJ XJ. So, you know, use the extensional strain. And again, this will all be in the notes. You can show that S is 20 pi over 3 times the viscosity times eta cubed times that matrix there. And then working out what the stress is in terms of the stresslet, we see that the viscosity is going to be the bare viscosity times 1 plus 5/2 times the volume fraction. So that's that first order correction that Einstein calculated to the viscosity in a very dilute suspension. This doesn't work very well. It has to be very dilute for this to be accurate, but it's still interesting. Okay, so I'll stop there. No, it doesn't have to be moving. The Stokes dipole doesn't have anything in it that tells it to move.
Just trying to understand what, not a swimmer, what is it? I'm trying to understand how the relation to this.
Yep. So over there, when we're talking about a passive sphere, if you've got an extensional flow, even though that's not going to tend to make the sphere move, if it's right in the middle, you still have to satisfy the boundary conditions at the surface. And that's what generates this. Okay. The swimming part, we just have to add that on top of it. We have to add the swimming velocity, like we did in Lighthill, that very first term, that 2/3 B1, that was just added to the stresslet. What this tells us about is how the swimmers interact.
You were writing down that free tensor. I was expecting you to write down the epsilon symmetric tensor.
Yeah,
And you didn't.
that should be in here.
Well, I guess mathematically it's not there, but I was wondering if there was some symmetry reason. I can see it. It's not.
Well, it is going to come in here, the antisymmetric part, if there's a torque.
Epsilon ijk.
Yep, I can write this with epsilon ijk for sure. Yep, and I sped through. It's actually in the notes. That part, there it is. It's right there. Yep. Oh, it's just an application of the stresslet. So maybe the simplest application of the stresslet is once you know Bachelor's result that this stresslet tensor S tells us what the mean contribution to the stress is, then you can calculate what the change in the viscosity is, because we can see that in addition to the usual stress that we have in a shear flow, there's another piece which is proportional to the stresslet. What I sped through very quickly is that you can relate S and the far field strain field to see exactly that you can write it all as an effective viscosity, which is the 1 + 5/2 volume fraction. Yes, so the question is, swimmers with chirality, like the E. coli, you would have, still you have no net torque, but you'd have to take a derivative of this to get the Roetlet dipole. So it would go, instead of like 1/r², to go like 1/r³. So it's usually a smaller contribution than the stresslet part. There are magnetic swimmers, artificial swimmers, where people have a rotating magnetic field to drive swimmers, and then you would have this without, at the 1/r². So I saw a hand over there somewhere. Phi. Sorry, again, I went too fast. So phi is the volume fraction. So it's n times 4/3 pi a cubed.
So how many does it have?
So the question is how well does this work? I think phi has to be like 3% for this to be accurate. It's not very accurate. Yes, the question is, I think, what is this A to 0? A to 0 is the viscosity of the solid. Yeah, again, this is only valid. This is valid. This this Einstein's calculation is valid for passive particles, very low concentrations. So all these interesting things that people see for how the viscosity changes, shear thinning, this cannot capture it because we're using this dilute approximation. Well, this works whether or not it's passive. We'll talk about that next time. Oh, I don't know enough about suspensions to not say that, but for swimmers, I think it's true. Okay.